Well, thank you very much, David. My talk tonight is not about magnetic monopoles, it's about information, quantum information. When we think about information nowadays, we're often reminded of the spectacular advance of our information technology, like this laptop that I have here, which seems like a hot machine. But we all recognize that the technology that seems impressive to us today is going to be surpassed in the future by new technologies that we can't really expect to be able to imagine today. Even so, it's interesting to speculate about technologies of the future. And I'll admit I'm not the ideal person to engage in that kind of speculation, since I'm not an engineer, I'm a theoretical physicist, and I can't claim to be deeply knowledgeable about how my computer works. But I do know, as a physicist, that the crowning intellectual achievement of the last century was the development of quantum theory. And it's natural for a physicist to wonder how the development of quantum theory in the 20th century will impact the technologies of the 21st century. To a physicist, information is something that we can encode and store in the state of some physical system, like the pages of a book. But deep down, all physical systems are really quantum systems, governed by the principles of quantum theory, and therefore information is something that we can encode and store in a quantum state. Physicists have recognized for a long time that information carried by quantum systems has some notoriously counterintuitive properties, and so we proudly speak of the weirdness of quantum theory, and physicists relish that weirdness and take great pride in it. But in recent years, we've also beginning to ask whether it's possible to put the weirdness to work, to exploit the unusual properties of quantum information to perform tasks that wouldn't be possible in a less weird classical world. The desire to put the weirdness to work is driving the emergence of a new field, what we call quantum information science, which, from my perspective, derives much of its intellectual vitality from three central themes or ideas: the ideas of quantum cryptography, quantum computation, and quantum error correction. Quantum theory itself is an old subject, over 100 years old now, but these ideas have begun to draw substantial attention only in recent years. And my goal tonight is to introduce you to these three themes of this emerging field, quantum information science. To get started, let's recall some basic facts about information. We know that any amount of classical, ordinary information can be expressed in terms of indivisible units, what we call bits of information, where we might envision a bit as an object, like a ball, say, which can be either one of two colors, like red or green. Since bits are valuable, we sometimes store them carefully. I can use a bit box, and I can deposit my bit inside the box, and then later on, when I open the box, the color ball that I put in comes out again, so we can recover a bit and read it. Now, quantum information, information carried by a quantum system, can also be expressed in terms of indivisible units, what we call quantum bits, or qubits for short. And for our purposes tonight, we can envision a qubit as, again, a ball stored inside a box, but where now we can deposit the ball inside the box through either one of two complementary doors, labeled door number 1 and door number 2. These two doors correspond to two complementary ways in which we can prepare or measure the state of some simple quantum system, like the state of a single atom or a single photon, particle of light. But let's not worry about that. Let's just think of it as an object stored in a box with two doors. Well, I can store information in a quantum box through door 1 or door 2, and then later on, when I open the same door again, the color ball that I put in comes out again, just as though the information were classical. But if, on the other hand, I store information in one door, say door number 1, and then later on I open the other door, the complementary door, then what comes out of the box is actually completely random and unpredictable. It has a probability 50% of being red, a probability 50% of being green, and has nothing to do with what we put in the box. So let's see it again. Here I put information into the qubit through door number 2, and if I open door number 2 again, the color ball that I put in comes out again, so we can recover a bit. But if I store information through door number 2, and then later on I open door number 1, then what comes out is random and completely unpredictable. That means that in order to read quantum information, you have to do it the right way. And if you do it the wrong way, you'll unavoidably damage the information. We can appreciate a consequence of that property of quantum information if we think about what it would mean to copy a quantum state, to copy a qubit. What would it mean? It would mean that if I had stored information in my qubit through door number 1, and then the copier built a duplicate box, then when I open door number 1 on the original and the duplicate, the color ball that I put in should come out of both of the boxes. And if, on the other hand, I happen to have stored information through door number 2, and then I build a duplicate box, then if I open door number 2 on the original and the duplicate, the color that I put in should come out of both boxes. But in fact, there's no such qubit copy machine. There isn't any physically realizable device which can copy the unknown state of a qubit. And the reason why not, at least roughly speaking, is that in order to copy the information that's inside the box, the copier has to look inside. And if it guesses right and opens the right door, the door that I use, then it'll be able to copy the information just as though it were classical. If it's wrong and opens the wrong door, then it will damage the information, and there will not be any way to build a high-fidelity copy. So while we might be able to clone a sheep, we can't clone a qubit. An example of a physical realization of a qubit is the polarization state of a single photon, a particle of light. The photon has an electric field which can be aligned either horizontally or vertically. That's a choice of polarization, and those two states are perfectly distinguishable. But alternatively, I could consider storing information by preparing a polarization state which is rotated by 45 degrees away from the horizontal or the vertical. These polarization states correspond to storing or measuring the photon through door number 1, these two through door number 2. And if I've encoded information in the polarization state of a single photon, and you don't know how I've encoded it, then there won't be any way for you to make a perfect copy of that photon, to clone the qubit, to clone the photon. Now, this is an example of quantum weirdness, and we can ask whether it can be put to work. In fact, the property that we can't copy quantum states without disturbing them does have applications in quantum cryptography. Let's say that Alice here wants to place a phone call to her friend Bob, but it's a private call, and Alice and Bob are concerned that their nosy friend Eve might try to listen in. Now, obviously, Alice and Bob should use some sort of code to foil Eve, but the trouble is that Eve, aside from being very nosy, is also very clever, and Alice and Bob aren't confident that they're smart enough to think up a code that Eve isn't capable of breaking. Except there's one way of encrypting information which is in principle unbreakable, which Alice and Bob can use if they share a secret key, a string of random bits that Alice and Bob both know and that Eve knows nothing about. Here's how it would work. Alice could take her important message and translate it into a string of bits shown in blue. And then Alice could use the secret key, shown in red, and bitwise add the blue message to the red key to obtain the encoded message or ciphertext. By bitwise, I mean when in the same place we have 2 zeros or 2 ones, we obtain a 0 in the black string, and if we have a 0 and a 1, or a 1 and a 0, we obtain a 1. Now Alice can send the black encoded message, the ciphertext, on to Bob. Bob also knows the secret key, the red string, and he can add it bitwise to the black ciphertext and recover the important message that Alice has sent. While the ciphertext is in transit from Alice to Bob, Eve might intercept it, and she might try to copy it down. But it actually does her no good, because the black ciphertext is completely uncorrelated with the message that's being sent. If she doesn't know anything about the red string, then she can't decipher anything about the message, even when she intercepts and copies down the ciphertext. So Alice and Bob can solve the problem of communicating privately, communicating securely, if they have a way of establishing a shared key, a string of random bits that they both know, and which they can guarantee Eve knows nothing about. And that's a problem that they can solve using quantum information, using qubits. Here's how it could be done. Alice could, first of all, generate a string of random bits. Think of it as a collection of balls, each of which is either red or green. And then Alice can decide at random to store each one of those bits in a quantum box, a qubit, decide at random to put it through door number 1 or door number 2, and then she closes up the boxes and sends them on to Bob. Bob receives the qubits, and he decides at random for each one of the qubits that he receives to open the box through either door number 1 or door number 2. So with probability 1/2, about half the time on the average, Bob will open the box through the same door that Alice used. And in those cases, Bob should find the signal that Alice sent, see the color that Alice prepared and put into the box. But with probability 1/2, about half the time on the average, Bob will open the wrong door, and in those cases what he finds is completely uncorrelated with the signal that Alice sent. But after Bob has opened the boxes and it's too late for Eve to interfere with them anymore, Alice can make a public announcement saying for each one of the signals that she sent whether she used door number 1 or door number 2. And then through public discussion, and it's all right if Eve overhears it, Alice and Bob can discard the cases in which they used different doors and keep the cases in which they used the same doors. And in that case, they should now have a string of random bits that they both share. Now what about Eve? When the qubits are traveling from Alice to Bob, Eve will attempt to extract some information from those boxes so she can learn something about the key. But at that point, Eve doesn't have any a priori information about whether door number 1 or door number 2 was used to conceal the information. And so if she collects some information about the qubits, she has to look inside some of the boxes, and she will sometimes look inside the wrong door. When she does that, she will damage the information in some way. So Alice and Bob can conduct a statistical test to monitor Eve's activity. They can sacrifice a portion of their key and compare to see if Bob really received what Alice sent as he should. And if they find a high error rate, if they find that what Bob received is different than what Alice sent a high percentage of the time, then they'll pessimistically assume that Eve has opened too many boxes and learned too much about the key. And in that case, they'll discard the key and not attempt to use it to encrypt a message. But if, on the other hand, they find that the error rate is sufficiently low, then they'll be highly confident that Eve hasn't collected very much information about the key. And in that case, we can actually prove that after some classical processing of the key to correct errors in it and to amplify its privacy, the final key is guaranteed to be such that Eve has negligible information about it. And that means it's perfectly safe for Alice and Bob to use that key to encrypt a message. And furthermore, the security is guaranteed for any possible eavesdropping attack that Eve might have used consistent with the known laws of physics. So in this scheme, which is called quantum key distribution, the security, the privacy, is really founded on principles of fundamental physics, the principle that we can't copy unknown quantum states without disturbing them. Whereas in most of classical cryptography, which is in current use, the security is based on an assumption that Eve has limited computational power. That is, there's some computation that she in principle could perform which would break the code, but we assume that that computation is too hard for her to perform in practice. This scheme of quantum key distribution has been demonstrated experimentally by sending single photons as qubits through optical fibers, the same kind of optical fibers that are used in telecommunication. And that's been done over distances up to about 100 kilometers and a little bit beyond, which is the current limitation imposed by losses of photons in the fibers. And in fact, quantum key distribution is now commercially available. Quantum key distribution systems are being offered for sale by several commercial companies, though I think it's fair to say that the technology has not yet proved its viability in the marketplace. So we've seen one way in which the weirdness of quantum information can be put to work, can be put to use. But we haven't yet encountered the really deep ways in which quantum information is different from classical information. That can only be appreciated if we consider states of 2 or more qubits. So let's suppose we have 2 qubits, and they can be far apart from one another. One, let's say, at Caltech in Pasadena, the other in the custody of my friend in the Andromeda galaxy. Some time ago, when both of these qubits, both of these boxes were still on Earth, I prepared them in a quantum state which has some unusual properties. Namely, I can open my box in Pasadena through either door number 1 or door number 2, and either way what I find is completely random and unpredictable. Has probability 50% of being red, 50% of being green. And the same is true for my friend in Andromeda. He can open door number 1 or door number 2, and what he finds is completely random and unpredictable. But that means that neither one of us, by opening his box, actually acquires any information. And that's kind of strange, because with 2 boxes we should have been able to encode 2 bits of information. Where is that information hidden? The answer in this case is that actually all the information is in correlations between what happens when you open a box in Pasadena and you open a box in Andromeda. When I open my box, the color that I find is random, but if my friend opens the same door, if, say, we both open door number 1, and I see a green ball, he's guaranteed to see a green ball too. And if I see a red ball through door number 1 and he opens door number 1, he's guaranteed to see a red ball. The same thing if we both open door number 2. The color that I see is random, but my friend is guaranteed to see the same color if he opens the same door. Now, there are 4 distinguishable ways in which a box in Andromeda could be correlated with a box in Pasadena. We could either find the same color or different colors when we look in door number 1 or door number 2. And we've chosen one of those 4 ways. That's 2 bits of information, which has been encoded in the boxes. But what's unusual in this case is that all the information is encoded non-locally. It's shared equally between the distantly separated boxes, and none of it is accessible if we look at the boxes one at a time. This property of quantum information, that it can be stored non-locally, shared equally between these 2 distantly separated qubits, is what we call quantum entanglement. And it's the really crucial way in which quantum information is different from classical information. Of course, correlations themselves are not so unusual. We encounter them all the time in daily life. Usually, I wear 2 socks which are the same color. And that means that if you look at one of my feet, then you know with near certainty what color sock to expect before you look at my other foot. And it's kind of similar with the qubits, with the quantum boxes. If I want to know what color ball my friend will see when he opens door number 1, I can open door number 1 on my box in Pasadena, and if I want to know what color he'll find when he opens number 2 in Andromeda, I can open number 2 in Pasadena. So it seems like it's almost the same thing, but in fact, the boxes are not the same as the soxes. They're fundamentally different. And the essence of the difference is that there's just one way to look at a sock, but we have these 2 complementary ways to look at the box, and that means that the correlations among the qubits are richer and much more interesting than correlations among classical bits. This phenomenon of quantum entanglement was actually first discussed in a paper by Einstein in 1935. This was 30 years after Einstein's great 1905 contributions, a paper that he wrote with his collaborators, Podolsky and Rosen. And it was really the last paper of Einstein's career which had an impact that we still feel today, although he remained scientifically active for another 20 years up until his death. To Einstein, quantum entanglement was very unsettling. It seemed to indicate to him that something is missing from our current understanding of the quantum description of nature, and so Einstein, Podolsky, Rosen called their paper, "Can the quantum mechanical description of physical reality be considered complete?" Their paper stirred a number of interesting responses, including one especially insightful one by Erwin Schrödinger. Schrödinger actually suggested the word entanglement to describe this phenomenon, and as he put it, the peculiar situation is the best possible knowledge of a whole does not necessarily include the best possible knowledge of its parts. I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So what Schrödinger meant here is that even if we have the most complete possible description of our pair of qubits, we're still unable to predict what will be found when we look at one of the qubits through either door number 1 or door number 2. And he added it as rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy, in spite of his having no access to it. And what he meant here is that the two qubits are very far apart from one another. One is in Pasadena, the other in Andromeda. But it's up to me, by deciding to open door number 1 or door number 2, to decide whether my friend will find some definite color when he opens door number 1 or door number 2. The theory of entanglement did not advance very much for the next 30 years. But the next important step was taken by John Bell. And starting with Bell in 1964, we began to think about entanglement in a different way, not just as something that's very strange, but as a resource that we can use to do useful things. I won't explain the details, but what Bell did is he described a game that two parties can play, Alice and Bob, say, where Alice and Bob are on the same team, they're trying to cooperate, and in order to win the game, they have to make correlated moves that are correlated with one another. But under the rules of the game, Alice and Bob are not allowed to communicate with one another after the game begins. And what Bell showed is that if Alice and Bob are provided with correlated classical bits at the beginning of the game and they play their best strategy, then they can win with a certain probability, 75%. But if instead they're provided with entangled qubits at the beginning of the game and they play their best strategy, they can win with a higher probability of success, above 85%. So in this sense, the quantum correlations, the entangled qubits, are a resource that can be used to do something useful to Alice and Bob, something that they couldn't do in the classical world. And experimental physicists have played this game, and they've won with a higher probability, which Bell said follows from the predictions of quantum mechanics. So it seems that these strange non-local correlations really are part of the correct description of nature. Einstein didn't like quantum entanglement. He derided it as spooky action at a distance, which sounds even more derisive when you say it in German. But a great thing about science is it doesn't actually matter what Einstein thinks. Nature is the way she is, as revealed by experiments. And once the experimental results are known, we have to accept that the non-local correlations really are part of the way nature behaves. Now I'd like to explain in a little more depth how the boxes are different than the soxes, why the quantum correlations are really different from classical correlations. And to do that, I'd like to tell you about another friend of mine who has 3 feet. Now my friend always wears every day an even number of red socks, sometimes 2, sometimes 0, but he never wears 1 red sock or 3 red socks. He wears an odd number of green socks and an even number of red socks. And that means that as soon as you look at 2 of my friend's feet and you see, for example, a green and a red sock, then you know for sure before you even look that you'll find a red sock on his other foot, because the number of red socks has to be even. And if you look at 2 of his feet and you see 2 red socks, then you know that the third foot has to have a green sock. If you see 2 green socks, then you know that the third foot has to have a green sock, because the number of red socks can't be 1 or 3. It has to be an even number. Now, I have 3 qubits which are distantly separated from one another. 1 is in Pasadena, 1 in Chicago, and 1 in New York. And some time ago, when all of these qubits were together in Pasadena, I prepared a particular type of quantum state of the 3 qubits with an interesting property. The property is that whenever I open door number 1 on 2 of the boxes and door number 2 on the 3rd box, I always find an even number of red balls. The box for which I open door number 2 can be any one of the 3 boxes, but I know because I've checked it over and over again a million times on identically prepared quantum states that whenever we open door number 2 on one of the boxes and door number 1 on the other 2, we have to see an even number of red balls. Oh, in this case, I opened door number 2 in Chicago and door number 1 on the other 2 boxes, and I found 0 red balls, an even number. In this case, I opened door number 2 in Pasadena, door number 1 in Chicago and New York, and I saw 2 red balls. In this case, I opened door number 2 in Chicago, 2 red balls. And that means, since we've checked this a million times and we know it's true, that if I'm interested in finding out what will happen when my friend opens his box through door number 1 in New York, then we can open door number 1 in Pasadena and door number 2 in Chicago. And if we see a green ball and a red ball when we do so, then we know for sure, before we've even opened the box, what will happen when we open door number 1 in New York. Namely, what will happen when we open door number 1. It has to be a red ball because it has to be an even number. It worked. On the other hand, if I'm interested in what would happen in New York when door number 2 is open, we can open door number 1 in Pasadena and Chicago, and if we see 2 green balls, then we know for sure that when we open door number 2 in New York, we must see what? It's got to be green, because we can't have just 1 red ball. It has to be an even number. Okay. Now here's something, though, that I've never attempted before. What would happen if we opened door number 2 on all 3 boxes? I'm going to do this experiment for the first time ever tonight here at the KITP. But to make the experiment more interesting, let's see if we can make some prediction about what we expect to happen. Well, how can we make a prediction? To get started, let me suppose for now that if I were to open door number 1 on all the boxes, then I would see 3 red balls. Now, I don't really know that for sure. Let's just suppose it for now, for the sake of argument. Well, if I knew it's the case that I would see 3 red balls when I open door number 1 on all the boxes, then I know it must be the case when I open door number 2 on all the boxes that I see 3 green balls. Why is that? Well, we can reason as follows. We know that if we open door number 1 in Pasadena and Chicago and we see 2 red balls, then we have to see a green ball when we open door number 2 in New York. We know that because we've checked it a million times. We don't need to check it again. And likewise, we know that if we open door number 1 in Pasadena and New York and we see 2 red balls, then we have to see a green ball when we open door number 2 in Chicago. And so on. We also know we have to see a green ball when we open door number 2 in Pasadena by the same reasoning. Everybody buy that? Okay. Of course, I don't really know what's going to happen if we open door number 1 for all 3 boxes, but something has to happen. And there's a limited number of possibilities. There are only 8 possibilities, and we can list them all. So, for example, if I knew that when we open door number 1 on the 3 boxes that we would see red, red, green, then I'd be able to infer that I'd have to see red, red, green when I open door number 2 on all the boxes. You see how the reasoning goes? It's the same idea as before. Because I know if when I open door number 1 in Pasadena and Chicago and I see red, red, then it's guaranteed that I have to see green when I open door number 2 in New York. And when I open door number 1, and we know this because we checked it a million times, in Pasadena and New York and I see red, green, then I've got to see red when I open door number 2 in Chicago. Okay? So if I guess that I see red, red, green when I open door number 1 on all the boxes, then it must be the case that I would see red, red, green when I open door number 2 on all the boxes. And now I can just list all of the 8 possibilities, and for each of the 8, use this type of reasoning to infer what I would see when I open door number 2 on all the boxes, given some hypothesis about what I would see if I opened door number 1 on all the boxes. So this is a good homework exercise that you can do later at home. But the result of the exercise is quite interesting. For every one of the 8 possibilities for what could be seen if we opened door number 1 on all the boxes, we find the prediction that when we open door number 2 instead, we have to see an even number of red balls. Sometimes it's 0 and sometimes it's 2, but we never get 1 red ball and we never get 3 red balls. Okay? So that's our prediction. Let's review what we did. We know, because we've checked it a million times and there's no doubt about it, that if we open door number 1 on 2 of the boxes and door number 2 on the 3rd box, we have to see an even number of red balls, right? And then by what appears to be unassailable logic, we inferred that if we open door number 2 on all the boxes, then we have to see an even number of red balls. Okay? So, we know what our prediction is. Let's do the experiment. Well, this is kind of embarrassing. Didn't I say that it was supposed to be an even number of red balls? But probably it's just an experimental error, because these experiments with the qubits are very delicate, so we should repeat it just to make sure. It's an odd number of red balls again. It was supposed to be an even number. All right, let's do it one more time to make sure. An odd number of red balls again. We do the experiment over and over and over again, and every time we find an odd number of red balls. Okay? Just the opposite of what we predicted in every single trial. This is really strange. Okay, so what did we do wrong? What was our mistake? Well, we've learned an important lesson, and one way to describe the lesson is that we can be seriously misled if we reason based on things that might have happened but didn't actually happen. That is, if I'm going to look inside a quantum box, if I'm going to measure a qubit, I have to make up my mind to open door number 1 or door number 2. I can never do both, not even in principle. Once I've opened door number 1 and I've seen the color of the ball, I can never really go back and check what would have happened if I had opened door number 2 instead. It's just not possible. Yet we used reasoning in which we say, suppose when I open door number 1, I would see a green ball, then if I opened door number 2 instead, I would have to see a red ball. That kind of contrary to fact reasoning, reasoning on the basis of things that might have happened but aren't actually what happened, we use it all the time in the classical world, and it serves us well. It leads to valid conclusions. But what we've learned is that type of reasoning can't be used to predict the behavior of quantum systems. These quantum systems obey a peculiar logic of their own, which the human mind doesn't seem to be very well equipped to grasp. So this should really bother you. This is disturbing. This is really the essence of what's weird about quantum information. Now let's think about how we can put it to work. For that purpose, let's think first of all about the complexity of information. Imagine that we have 10 classical bits. We have 10 boxes, each of which has a colored ball inside. Of course, there are a lot of ways in which the balls could be put inside the boxes. 2 to the 10, 1,024 ways. But for any one of those ways, I can describe it to you very succinctly. Each ball is either red or green. I just give you a list of 10 bits. But suppose, on the other hand, that I actually have 10 qubits, 10 quantum boxes. And now it's not quite fair to say that each box contains a red ball or a green ball. We've learned that that's not the right way of thinking about things. Rather, each box has some potential to be red, some potential to be green. And what I find when I open one box through door number 1 or door number 2 will be correlated with what I'll see if I open door number 1 or door number 2 on another box. So for one typical state of these 10 qubits, to give a complete description of all those correlations requires that I write down a lot of classical information. A number of numbers of about 1,000 to describe all the correlations with just 10 qubits. And as the number of qubits increases, the complexity of that description explodes, so that if I have 20 qubits, just to write down a complete description of all the correlations of 20 qubits with one another, I would have to write down about 1 million numbers. And for 30 qubits, for one typical state of 30 qubits, I'd have to write down 1 billion numbers to characterize all those correlations. With a still rather modest number of qubits, like 300 or so, for one typical state of the 300 qubits, if I wanted to write down, in terms of classical bits, a complete description of all the correlations, I'd be required to write down more numbers than the number of atoms in the visible universe. So it'll never be possible, even in principle, to write that description down. That property of quantum information, that we can't represent it in any reasonable way using ordinary classical bits, was very intriguing to the physicist Richard Feynman. And it led him, about 25 years ago, to ask the question, could it be that if we had a computer that operates on qubits rather than bits, a quantum computer, it would be able to perform tasks that are beyond the capability of any conceivable classical computer? What Feynman had in mind is that if we can't even hope to write down with classical information the state of the quantum computer, then perhaps by processing the qubits we can perform a task that a classical computer could not possibly emulate. Well, if we want to think of what sort of computational power the quantum computer might have, we should think of a problem which is hard for classical computers. You're familiar with the concept of a prime number, a number that's divisible only by itself or by 1. And with prime numbers we can play a game. It's a game just like Jeopardy! I give you the answer to a multiplication problem. I obtain that number 15 by multiplying together 2 prime numbers, and you're supposed to tell me what the question was. What prime numbers did I multiply together to get that answer? And you would be able to tell me the prime numbers have to be what? 3 and 5. And if I told you that 91 is a product of 2 prime numbers, you'd be able to tell me that those numbers are? Anybody? 7 and 13, right. But as the numbers grow, the difficulty of the game increases rapidly, so that if I told you that 2,537 is a product of 2 prime numbers, you'd be able to tell me that those prime numbers are what? Any lightning calculators out there? Okay, sorry, time's up. But if I had given you a pencil and a piece of paper in a few minutes, you would have been able to tell me that I have obtained 2,537 by multiplying together 43 and 59. But the difficulty of the problem accelerates very rapidly as the number to be factored gets larger. So if I told you that I obtained this 130-digit number as a product of 2 65-digit prime factors, that's a very hard computational problem. It would stretch today's supercomputers pretty much to the limit. It would take several months of crunching away to find out that this is the answer. Factoring is a hard problem. And when the numbers get even bigger, it just becomes completely intractable, even with the best computers we have. So here's an instance where we can ask, could the quantum computer do better? Finding the prime factors of a number is sort of like looking for a lock, looking for a key that opens a lock. Once we have the right answer to the problem, we can easily verify that the key fits, that we have the right factors, because it's easy to multiply numbers together to find their product. But if we try to find the factors by testing one trial pair of factors after another until we finally have the right answer, we can never solve the problem in any reasonable amount of time that way. That's why it's a hard problem. With a quantum computer, we're able, in a sense, to try a vast number of keys and a vast number of locks all at the same time. The secret of the quantum computer is a kind of massive parallelism. If we perform a computation on qubits once and only once, we can, at least for some purposes, perform the same task as if we had performed the calculation over and over again a vast number of times on, say, a few hundred bits, a number of times as large as the number of atoms in the visible universe. So what does that mean in practice? The hardest factoring problem that's ever been solved is factoring a 193-digit number. That was just done a few months ago. And it took 30 years of CPU time with a pretty fast processor. It was, of course, a highly parallelized computation. And from what we know about the hardness of factoring, we can estimate that with that same hardware, if we wanted to factor a 500-digit number, it would take longer than the age of the universe. So even with vast improvements in technology, we don't expect to be factoring 500-digit numbers with ordinary digital computers in the foreseeable future. But suppose that we had a quantum computer which is just as fast as this classical computer, a gigahertz quantum computer. We have to suppose that for now because we don't have that yet. But if we did, then we'd be able to factor the 193-digit number in a second and the 500-digit number in just 20 seconds. The time required to solve the problem scales in a radically different way when we use the quantum computer because of the power of this quantum parallelism. So perhaps you'd concede that a quantum computer, if we can manage to build one, would be a very ferocious computing machine which could far outperform digital computers of the foreseeable future. So why don't we just build one of these things? What's stopping us? Well, it's really, really hard, and I'll come back to that in a few minutes. But we might ask, apart from the technical problems, are there issues of principle which will prevent us from ever building large-scale quantum computers? Just wanted to make this comment. So what we've seen is that while factoring is a very hard problem for classical computers, for quantum computers it's easy. Factoring is not much harder for a quantum computer than multiplying two numbers together to find their product. And that's really an amazing thing, that the distinction between a hard problem and an easy problem, a problem that we'll never be able to solve even with enormous improvements in technology, and a problem that we can expect to be able to solve someday when our technology is advanced enough, the difference between those two is different than it would be because this is a quantum world, not a classical world. That's what the factoring problem tells us. Okay, so now what about the question, is there some problem of principle that will prevent us from ever achieving large-scale quantum computations? What comes to mind is the problem of errors. Quantum computers are much more susceptible to making errors than ordinary digital computers. Physicists sometimes like to say that we can imagine a quantum state of a cat, which is a superposition of the live and dead state of the cat. That is, it would be a state which is not completely dead or completely alive, but rather like the ball in the box, which wasn't really red or green until we opened the box. But we never really encounter cats which are partly dead and partly alive like this. We don't see such superpositions of macroscopically distinguishable objects in everyday experience. And the reason why not is that no real cat can be perfectly isolated from its surroundings. And the interactions with the environment, in effect, immediately measure the cat, open the box, turning it into a state which is either completely dead or completely alive, like definitely red or definitely green. We call this phenomenon in which a quantum state, which is partly dead and partly alive, becomes definitely dead or definitely alive, decoherence. And decoherence is actually rather important for understanding why it is that we don't see quantum phenomena in our everyday lives. We do observe quantum effects in microscopic systems that we can study in the physics lab, like individual electrons or individual atoms or photons. We don't see quantum effects in the macroscopic physical systems that we deal with every day. And the reason why not is decoherence. The interactions with the environment, in effect, hide the underlying quantum phenomena and make the world appear to be classical. Now, a quantum computer won't otherwise be so much like a cat, but like a cat, no matter how hard we try to prevent it, the computer will inevitably interact with its environment, causing decoherence. And that means that the information carried by the computer will be damaged and our computation will fail. So it's only if we can find some way of protecting a quantum computer from decoherence and other possible sources of error that we can expect to successfully realize large-scale quantum computers. Now, errors can be a problem even in the classical world. We all have bits that we cherish, but everywhere there are dragons lurking who delight in tampering with our bits. But in the classical world, we've learned some ways of fending off those dragons. If I have some bit that I value very highly, I can store some backup copies of the bit, and then if a dragon comes along and changes the color of one of the balls, I can employ a busy beaver who frequently checks the balls to see if one is a different color than the other two, and when that is the case, he immediately repaints that ball so that all three match again. So as long as the dragon hasn't had a chance to flip the color of two of the three balls, the beaver will be able to recover the stored information because it's been stored redundantly. And we'd like to use that same principle, that redundant storage protects against error. We'd like to apply that to quantum information. But it appears at first that there are difficulties. As we've already noted, we can't copy unknown quantum states accurately, so we can't simply take the qubit that we want to preserve and store a backup copy in case the original gets damaged. Furthermore, there are more things that can go wrong with qubits than with bits. Our dragon could open door number 1 of our quantum box and change the color of the ball, and then reclose the box. That would be like a bit flip error that occurs in the classical world. But he might instead open door number 2 of the box and change the color of the ball, and then reclose the box. That we call a phase error acting on the qubit. It really has no classical analog, yet we need to be able to protect against both kinds of errors if we want to preserve quantum information. Another way of thinking about the phase error is this. We can imagine that the dragon opens door number 1, and he doesn't flip the color of the ball, but he just observes the color. In this case, he notes that it's red, and he remembers that it's red, and then he closes the box again. Now, if he hadn't noticed whether the ball was red or green, then after reclosing the box, there wouldn't have been any damage, and our qubit would be intact. But he kept a record of whether it was red or green. He, in effect, copied the qubit, and as we've seen, that copying necessarily damages the qubit in a way that can be discerned if we open door number 2. That's a phase error. And typically, it's easier to observe and remember the value of a bit than it is to flip a bit, and that's why phase errors are particularly pervasive and difficult to fend off in complicated physical systems. If we want our quantum computer to work successfully, if we want to resist the destructive effects of decoherence, what we need to do is to prevent the environment from learning about the state of the quantum computer and recording that state during the intermediate stages of the computation. In order for the quantum computer to work its magic, there must not be any record left behind about what the computer was doing between the beginning of the computation and when the final result was read out. If such information does get recorded, that will cause decoherence and cause the computation to fail. But in fact, we've learned how to prevent information from being recorded in the environment, and so to stave off decoherence and protect a quantum computer. Suppose I have one qubit that I want to preserve. It doesn't work to do what we did in the classical case, to store that quantum information in a state of 3 qubits. But actually what I can do is encode the quantum information in 1 qubit in a correlated state of 5 qubits. Store the information in non-local correlations in entanglement shared by 5 qubits. And we do that in such a way that the information that's been stored in the block of 5 is not accessible if you look at the qubits one at a time. So the dragon might come along and damage one of the boxes in an arbitrary way, and in doing so he might learn about the contents of that box. But learning about the contents of one box doesn't tell him anything about the encoded information, and therefore the damage is reversible. We can now have the beaver come along and perform collective measurements on the 5 qubits. He doesn't look at the qubits one at a time, but make some kind of collective observation on all 5 qubits at once. If you have a quantum computer, you can do that, and the information that he collects enables him to diagnose which one of the qubits has been damaged and what needs to be done to reverse the damage. When the beaver carries out this recovery operation, he also doesn't learn anything about the value of the encoded qubit. He only learns about the errors and reverses them. And because he doesn't know the value of the qubit, there need not be any damage to the qubit. There isn't any record left behind in the environment of what state the qubit is in. So this type of scheme enables us, through a clever kind of redundant storage, to protect against quantum errors. And the scheme can be scaled up to protect many qubits from many errors. Now what about the hardware in a quantum computer? What is the hardware actually going to look like? Well, in fact, there are a lot of different approaches to quantum hardware that are being pursued in physics laboratories around the world. And I'll just tell you about one of those approaches, which is the most advanced at this stage, and that's the ion trap quantum computer. The technology exists to trap and hold charged atoms, ions, using electromagnetic fields, and to keep the ions in the trap for a long time. We can think of each ion as being in either one of two distinguishable states. Let's say either in its ground state, its lowest state, or some higher energy excited state, which is particularly long-lived. So we can think of the ions as being qubits, having two distinguishable states, which we might as well represent, again, as red and green balls. Now you might think that because these are individual atoms and they're very tiny, that it would be hard to read out the state of the ion and see whether it's in the red state or the green state, so to speak. But actually that's not very hard. We can illuminate all the ions with laser light, and if we choose the frequency of that light appropriately, then if the ions are in the green state, the light won't interact with the ions at all and they'll remain dark. But if the ions are in the red state, they'll interact strongly with the light and they'll glow visibly. So I can read off a sequence of dark and bright ions to read out the state of a quantum computer. This is an actual photograph of ions, beryllium ions in this case, in an ion trap at the National Institute of Standards and Technology. In this case, the ions are separated from one another by about 10 microns, which is a long enough distance compared to the wavelength of visible light, so the individual ions can be easily resolved. Of course, we want to do more than just read out the state of our quantum computer. We want to process that quantum information. And here's how that could be done in an ion trap. We can address one of the ions with a pulsed laser, and if we choose the frequency and the duration of the laser pulse appropriately, then nothing will happen if that ion is in the red state. But if it's in the green state, it will undergo a transition driven by the laser to the red state, and a vibrational mode of all the ions in the trap will be excited. And then we can pick out another ion in the trap and address it with our pulse laser. And if we choose the frequency and duration of that pulse appropriately, nothing will happen if the ions have not been excited into a vibrational state. But if they are vibrating, that ion will undergo a transition from red to green, and the vibration will stop. So we picked out two ions in the trap, and if the first ion had been red, nothing would have happened. If the first ion is green, then two of the ions change color. That means that if the first ion started out in a superposition of red and green, a state which is not definitely red or definitely green, then this procedure would produce an entangled state of the two ions. It would produce a quantum correlation. And many such procedures in sequence can build up a complicated entangled state of many ions. This type of protocol has been carried out in several laboratories working with ion traps. So far, it's only been done on rather small scales. The largest entangled state that's been produced in an ion trap is a state of 8 ions. If we want to do something which is really computationally interesting, that can compete with what classical computers can do, we need to scale that up enormously, build entangled states of hundreds or thousands of ions. Scaling up an ion trap to a large system is a very daunting engineering challenge, but it might be possible. Now, in just the last few minutes that I have left, I would like to tell you a little bit about a radically different approach to building quantum hardware, which is the subject of a current KITP program. This different approach to building quantum hardware begins with the observation that if we're trying to protect a quantum computer from noise, it's useful to think about topology. What is topology? When a mathematician speaks of the topological properties of an object, he means the properties that remain invariant when we smoothly deform that object. So to a topologist, a donut is equivalent to a coffee cup. Both have one hole. The donut has a hole in the middle. The coffee cup has a hole through the handle. If we're thinking about how to realize a quantum computation in a way which is robust and resistant to error, that means we would like the way the quantum computer acts on quantum information to remain invariant when we smoothly deform the computation by introducing some noise, say due to interactions with the environment. So we'd like to use physical interactions to compute which have some kind of topological robustness. And such interactions are known in physics. For example, we know that if a charged particle, like a single electron, is transported around a tube of magnetic flux, the quantum state of the electron is modified in a particular way. We say it acquires an Aharonov-Bohm phase. But the important thing about this Aharonov-Bohm interaction is that it only depends on the fact that the electron wound around the magnetic flux tube. It remains invariant if we deform the trajectory of the electron. All that really matters is the winding number of the electron around the flux tube, that it went once around, a topological property. Now this type of topological Aharonov-Bohm interaction of an electron with a flux tube is not useful for information processing. But if we consider systems in two spatial dimensions, systems in which particles can slide around on a tabletop, in effect, then there are actually quite rich possibilities for the types of topological interactions that can occur. In a system in two dimensions, for particles on a table, it's possible to have exotic particles that we call anyons. Now, up close, all anyons look alike. Locally, they all look the same. But quantum information can be stored in the collective state of many anyons. The anyons can be patched together in different ways. And that quantum information can be processed by performing exchanges of the anyons, by having anyons swap positions. And in particular, the effect on the quantum state when, say, the first and the second anyon swap position is different than the effect when the second and third swap position. So by performing many such exchanges or swaps, we can process the quantum state in a quite complex way. So if we have a system of anyons, we can envision operating a topological quantum computer, an idea first proposed by Alexei Kitaev and elaborated by Mike Friedman and his collaborators. Kitaev and Friedman are two of the key participants in the KITP program on topological quantum computing, which is currently underway. We would initialize a topological quantum computation by making pairs of these particles, these anyons, and then the information could be processed by performing a sequence of exchanges of the neighboring anyons. And to visualize that process, we can think of lines traced out by the trajectories of the particles in two-dimensional space and time, here represented as the vertical direction. Those lines, those trajectories of the particles, weave around one another, defining some kind of braid. And then after we've completed executing this braid, we can read out the quantum state, complete the quantum computation, and read out the final result by bringing the particles together in pairs and detecting whether those particles annihilate one another and disappear or fail to annihilate and persist. Now the beauty of this idea is that the information is encoded in a highly non-local way. That means that it's very hard for the environment to find out what the state of the quantum computer is, and that makes the computation very resistant to decoherence. In fact, in order to get the right answer to a computation, all that's essential is that the particles execute the right braid. The computation has a kind of topological robustness. How can we actually realize anyons, and what type of physical system might they occur? Well, there are physical systems in which we believe there are anyons, including the systems that exhibit what is called the fractional quantum Hall effect. These are systems where electrons are confined to move in two dimensions at, say, an interface between two semiconductors. And if we put these electrons moving on a table in a very high magnetic field, which enhances their interactions with one another, and we make the system extremely cold, put it in a very good refrigerator, then these electrons can find a very exotic, highly entangled quantum state. This state is a new phase of matter with very unusual properties. In particular, the particle excitations in this new phase of matter, although they're in a sense composed of ordinary electrons, are profoundly different than electrons. They are, in fact, anyons, which have topological interactions. And indeed, they even carry electric charges, which are fractions of the charge of an electron. The topological interactions among anyons have never been directly observed in an experiment, but that should be possible in the very near future. And when the signature of anyons, the topological interactions, are first confirmed experimentally, that'll be an exciting development for basic physics, but it will also be a demonstration of a primitive element of a topological quantum computer that might conceivably be scaled up to perform hard computations. So, I've told you about how qubits are different from classical bits, why the boxes are different than the soxes. I've told you that we can't copy unknown quantum states, which is the basis of security or privacy in quantum cryptography. I've told you that we can't succinctly describe a state of many qubits in terms of ordinary classical bits, which opens the possibility that quantum computers can perform computations which are not possible with ordinary digital computers. I've told you about how errors in a quantum computer can be controlled, and I've told you something about the pioneering efforts to achieve information processing, quantum information processing, in the physics laboratory. With each one of these achievements of quantum information science, there are corresponding challenges. In cryptography, we would like to understand what other possible applications are there for a quantum internet. What other types of communication or cryptographic tasks can be performed better if we use quantum information instead of classical bits. When it comes to computation, we would like to have a clearer understanding of just what quantum computers can do. What are the problems that are easy for quantum computers? We know some examples, but we have a lot to learn about what the power of quantum computing really is. We'd like to see the idea of quantum error correction fighting off the effects of decoherence realized in actual physical devices, and we'd like to conceive and eventually realize types of quantum hardware that are potentially scalable to very large systems. And meanwhile, as we're learning more about the information processing capabilities of quantum systems, we're getting new insights into basic physics, and I think many such insights will continue as this subject matures. So let me finish up with Einstein again. Einstein saw, back in the 1930s, sooner and more clearly than others, the essential weirdness at the core of quantum theory, what came to be called by Schrödinger quantum entanglement. And to Einstein, this was spooky action at a distance, which seemed to presage, at least as he saw it, the emergence of a deeper theory that would supersede quantum mechanics. But it's been 70 years now, and quantum mechanics, as it was already formulated in the 1920s, has successfully been confirmed in all experiments in which it's been tested. There's no evidence for a deeper theory that will replace quantum mechanics. But the insight of Einstein, Podolsky, and Rosen that quantum entanglement signifies a particularly profound departure from the classical description of nature has been very amply vindicated. And now we're facing the exciting challenge of putting that weirdness to work. Thanks a lot for listening.
Well, as always, the floor is open for questions. I'm sure there are many today. And please wait till I bring you the microphone so you can hear.
You mentioned the trapped ions as one hardware realization. I've read that an array of Josephson junctions is another potential way of realizing the hardware. Could you comment a little bit about the pros and cons of these two approaches and how far along we are?
Right. So the question is about alternative ways of building quantum hardware. I talked about an ion trap. Another way is to use superconducting devices. Josephson junctions are systems in which the behavior of superconductors can be very well controlled with appropriate electronics. And there are nice ways of encoding a qubit using superconductors. There are actually several different ways. But one is that we can have on a piece of superconducting material a superposition of two different values of the total electric charge, for example, which can be used as a qubit. That is, the charge can be either, say, 100 or 101 in units, like the twice the charge of an electron, and we can have a superposition of charge 100 and charge 101, which it behaves something like a ball, which is not definitely red or definitely green. But the question is, how do we compare these two schemes? What are the advantages and disadvantages of ion traps versus superconducting implementations of qubits? Well, one potential advantage of the superconducting realizations of qubits is the scalability. We know how to put on a chip many superconducting junctions. So if we can get one of those junctions to perform very reliably as a processing unit in the quantum computer, it might be possible to scale that up by quite a bit using fabrication technologies that already exist. The problem is successfully realizing quantum computation on small scales with these systems, because they're intrinsically noisier than the ion traps. What makes the ion trap special is it's a system where we have really exquisite experimental control over the various sources of noise, and those sources are understood in great detail in ion traps. In the superconducting materials, there are many complexities in understanding the noise, which have to do with the details of the materials from which the Josephson junctions are constructed. So there's a big challenge just achieving the material fabrication to good enough reliability to make a working element of a quantum computer. If that's successfully done, then the superconducting realizations might turn out to be very promising. Yeah.
I understand that chaos can reduce decoherence. Is that correct? And if so, could that be applied to a quantum computer?
So I think the question was, can chaos reduce
decoherence. Or reduce the rate of decoherence.
I guess I'm not really sure what you're referring to. Do you know? Oh, Zurich. Oh. Well, I think that quantum systems which exhibit chaos actually pose problems for controlling those systems, which go beyond the problems of control in some of the simple realizations of qubits that I was talking about, like in an ion trap or in superconducting junctions. So if we're going to realize a quantum computer, then we want to have the best possible control over the operations that are applied to the qubits. So there are really two issues which, to a certain degree, might compete with one another. One is the intrinsic decoherence, which is important if you want to have a quantum memory where you can store a qubit and keep it there for a long time, protected from decoherence. But another issue is we want to do processing. And systems which exhibit chaos are very hard to process in a controlled way. So it might not be a promising path for realizing quantum computation.
No more questions? Everyone understands? Or is it just too weird?
How do you think this fits in with Moore's law on the development of computational power? Do you think it could enable the continuation of Moore's law into the far distant future, or do you think it's possibly a completely new direction for computing?
I think of it more, well, okay, I think there are two aspects to the answer that I would like to give. The question is, how does this fit in with Moore's law? Moore's law is the observation that over a number of decades, our computational hardware, through large-scale integration, has improved at an exponential rate. And computing power tends to double every 1.5 to 2 years, and this is true going back to the 1960s. It seems that Moore's law will eventually, and fairly soon, hit a brick wall. Perhaps it's starting to happen already. And there's a fundamental limitation on how far conventional digital technology can advance, which comes just from the atomic scale. Because as the devices on a computer chip get smaller and smaller, the number of electrons which participate in the switching of a bit gets to be a number of order 1, and at that point it's hard to make things smaller and for them to still function. So one part of my answer is that I think the insights that we're getting into quantum information could be very relevant to continuing Moore's law at least a little further in ordinary digital computation. Because what becomes more and more of a challenge as the devices get smaller and smaller is to make the computer system behave classically so that quantum effects don't interfere with its performance. And as we understand things like how to control quantum systems better, we might be able to do classical computation a little better and a little longer. But eventually, I think we're still going to run into the brick wall. Quantum computing is really a different story, and there are still physics limitations in quantum computing that come from things like the size of atoms and the fact that we can't split electrons. But it's a type of exponential advance in processing power that comes about not because we build better and better components that we can make smaller and smaller, but it's really a qualitatively different type of processing which has huge advantages, at least for solving certain problems. I don't think that it's likely, although maybe I'm wrong, that in the future we'll do all computation with quantum computers. There will still be some things that computers do which are important to us, like word processing and email, which we probably won't want to do with quantum computers. I think the quantum computer will be more of a special hot rod that you'll attach to your ordinary classical computer to solve certain problems that you'd never be able to solve otherwise.
On what basis have you estimated the possible performance of the quantum computers, since they have not been built yet?
I'm sorry, could you say it again?
On which basis have you estimated the possible performance of a quantum computer?
So is the question, how quickly do we expect this technology to advance?
No. You gave us estimate of time.
I see.
Computation of 500 years becoming 20 seconds.
Right, so the question is, when I said that the quantum computer would be able to factor a 193-digit number in 1 second and the 500-digit number in 20 seconds, where did I get those estimates? And the answer is that one can work out in detail the quantum algorithm that we need to run on a quantum computer in order to achieve factoring, and we can count the number of elementary steps in that algorithm. So I did that calculation by recognizing that about 1 billion operations would be needed to factor the 193-digit number just by counting them. And so I said if I had a gigahertz quantum computer, I'd be able to solve the problem in a second.
Again, so the main thing is how it scales. So if it took them 2 seconds, then it would take, instead of 20, 40 seconds. But it scales linearly instead of exponentially. Right.
The important thing is that the difficulty of solving the factoring problem scales like a power, essentially the third power, of the number of digits in the number to be factored. The classical algorithms scale in a much worse way, the time needed to solve the problem grows almost exponentially with the number of digits. And so it becomes completely infeasible when the numbers get much larger than a few hundred digits.
You should explain this is why you get this field is highly supported.
Yeah, that's right. I kind of evaded that in my talk. So in fact, factoring you might not think is all that important a problem. It's an interesting number theoretic problem, and there are other arithmetic tasks that we know quantum computers are good at. Actually, it turns out, oddly enough, that there are people who care a lot about how quickly computers can factor. And the reason is that cryptographic schemes that are in widespread use, that you've used yourself if you sent your credit card over the internet to make a purchase, are based on the difficulty of certain arithmetic tasks like factoring. And if we only have classical computers, those schemes seem to be very secure because the factoring problem that you need to solve to break the code is completely infeasible. But when quantum computers are readily available, then those schemes will no longer be secure. And what will we do then? Well, one thing we might ultimately do is turn to quantum cryptography, the scheme for encrypting information that I described, which is really based on principles of fundamental physics rather than the difficulty of the computation needed to break the scheme.
I don't know very much of quantum mechanics, but correct me if I'm wrong. I understand that in quantum physics, the observer has very much of influence of what is going to be perceived as a reality, even though there could be infinite possibilities of the other side, depending on the interaction of the observer. So in that case, I'm just trying to understand, creating a computer like that, the observer, meaning the person who works with that computer, since you mentioned that if there is an effect of the environment, there's also an error.
Right.
If there is an observer, or the dragon not knowing what is the color, or not guessing or even memorizing what is the color of the ball, it might have a better effect.
Right.
A better, it will allow that possibility to come up without an error. So are you trying to say that by minimizing the observer's control, a quantum computer will work better? I don't know if I'm explaining it well, but I'm trying to understand.
So the question is about the role of the observer in the behavior of a quantum system. We know that when we make measurements, we necessarily disturb a quantum system in certain uncontrollable ways, which is different than in the classical world, where we can collect information about the state of the system without disturbing it. And of course, that was the basis of part of what I was talking about when I told you about quantum cryptography, that we can't collect information about quantum states without disturbing them, whereas classically we can do that. But you were also asking about the idea of preventing errors in a quantum computer and what the role of the observer is there. And as your question suggested, if as a quantum computer is doing a computation, I'm watching it every step of the way to see how the quantum state is changing from one step to another, if I'm observing how the computation is proceeding, then the quantum computer won't work, or it will behave like a classical computer, like a computer in which, in principle, each step is known and could be recorded by someone making the observation. For the quantum computer to work, there must not be any record, even in principle, that someone can access that will tell you exactly what the quantum computer was doing during the computation. Though, of course, when we read out the final result, we have to have that in a form which we can record and write down and share with our friends. So in order for a quantum computer to work, if you ask it after the computation is over, quantum computer, what were you doing while you were performing this computation, factoring this 1,000-digit number? If everything went well, the computer should say, I forget. There shouldn't be any record that we can access of what was going on during the computation in order for it to work effectively. And this is really the trick to controlling errors in a quantum computer. We have to make sure that even in principle, no record is left behind of what the computer was doing during the computation. So the role of the observer is quite important here. Namely, we don't want to have an observer who knows what the quantum computer is doing while it's performing its task.
Well, to ask the question slightly different, I mean, I know the answer, but I wouldn't know how to explain it.
Uh-oh.
Which is, since, as you pointed out, in quantum mechanics you do many measurements, and all quantum mechanics can tell us is probabilities, how could we build a device that will get the right answer each time for a computational task instead of probability? Right answer.
Well, so I guess there are several ways of answering that question. One is that the probability could be close to 1. If we consider particular dynamics or the way the system is evolving, it may be the case that if we make the right measurement at the end, the answer is nearly deterministic and highly predictable. It's not true that all measurements you make on quantum systems give random results that are completely unpredictable. Fortunately, for the problems that we know about now, which are the most interesting ones that quantum computers can solve, that classical computers can't, when you have the right answer, it's easy to verify that the answer is correct. So if the quantum computer doesn't give the right answer to the problem every single time, but has some reasonably high probability of finding the right answer, since we can check the answer, that's good enough. And we have to run the computer perhaps some modest number of times before we finally get the right answer. But when we do arrive at the right answer, we know it's right, and we can halt our computation.
What role, if any, does Planck's constant play in the... I'm sorry. What role, if any, does Planck's constant play in the quantum computer game?
So the question is, what role does Planck's constant play in the theory of quantum computation? The Planck's constant is a fundamental constant in nature which controls how important quantum effects are. It tells us things like how small a quantum system has to be in order for the quantum effects to be important. And the smallness of Planck's constant is part of the explanation for why, in our ordinary experience, we don't see quantum effects. I think the short answer is it plays very little role in the theory. Planck's constant is important for answering questions like how do we understand the classical limit of a quantum system? You know, under what circumstances can we say that a quantum system can be well described by classical physics? But in quantum computation, we're very far from that regime. And we're so far away from the regime where the quantum physics is turning over, crossing over to classical behavior, that Planck's constant, for the most part, is not very relevant.
This is kind of a similar question to what David was asking earlier, but you were talking about error reduction and various means. I'm just wondering if you just let the system rip over and over, and you have these random errors at different qubits, is there a tendency to convergence toward a range of answers such that a few multiplications, talking about this prime factoring thing, where you just have to test out a few, in other words, to give you an area? Does that mathematically make any sense? Or
so is the question, suppose I didn't do the error correction at all,
yes,
but I just did the computation.
Did the computation, got an answer, and then did it again and see
right.
if it differed. And
right.
would there be any, would it tend to converge?
Yeah. If we don't do the error correction at all, but there is some noise present at some level, then we would be able to perform our computation successfully for problems that are small enough, like let's say factoring numbers that are not too large. But when the problem got to be sufficiently complex, eventually the noise would completely overwhelm the computer, and we would get results at the end of the computation that are essentially random and therefore useless. So the noise will always place some limit on how complicated a computation we can perform successfully unless we do something to control the effects of the noise.
So for big problems like what this computer is designed for, noise is very important to control.
Right. It's a fundamental issue.
Thank you. Can you give us just some, in as far as possible, some idea what such a computer might physically look like? You showed us 2 ions 10 microns apart. You need 1,000 ions in quantum traps.
Right.
Seems a pretty incredibly tiny device.
Right. So the question is, can I give you some idea what a quantum computer might physically look like? And I can make some guesses, but I might turn out to be wildly wrong. But let's suppose that we eventually achieve large-scale quantum computation using ion traps, as an example. There are just practical limits on how many ions you can put in a trap and still be able to perform reliable quantum operations in the trap. You probably wouldn't want to put more than about 10 ions in a single trap, because otherwise the vibration, the trap becomes too soft and it's too hard to resolve the different vibrational modes, for example. So there's some constant number of ions you would put in a single trap, let's say 10. And now if you want to scale up the computer, you would have to have many ion traps. But in order to do big computations, you would have to have those ion traps be able to communicate with one another to be able to swap ions back and forth. So we could imagine a system, and it would probably be some kind of nanofabricated system with microscopic ion traps, with passageways which allow us, in a controlled way, to move an ion from one trap to another, to spread the entanglement beyond the trap in which it's created so it can be shared with other traps. And probably, as you suggested, since we want to have thousands of qubits, we would have to have at least hundreds of these ion traps which are able to share ions with one another. Some of those capabilities have already, at least in a rudimentary way, been demonstrated. It's been shown in ion trap experiments that we can move an ion from one place to another without destroying the quantum states, without spoiling the coherence of the quantum states. But we'd have to have a very intricate system of control to keep hundreds of ion traps all performing accurately as they would need to. And we'd have to have a very complicated system of lasers to manipulate the ions in all the different traps, and some kind of electromagnetic channels that would move the ions from one place to another. It's kind of nice that they're ions because they have electrical charges, and that makes it easier to manipulate them in some ways with electronics. And because the information is really stored in the internal state of the ion, it can be pretty well protected even when we're moving the ions around.
Okay, I'm going to ask the last question, which I've asked John before, and every time I get a more optimistic answer, so I'll see what he says today. How long will it take?
So the question is, when will we actually have quantum computers? And I think what the question means is, when will quantum computers really be able to solve problems that we can't solve with ordinary digital technology? And the honest answer is, I don't know. If it were to happen in the next 20 years, I would consider that to be a big surprise. Okay. I do believe that it will happen during the 21st century. I think once you start talking about, 30 or 40 years, it certainly seems conceivable, but that's just sort of saying, I don't really know, because that's a long time. I do think that some of the technologies that are already developed at a small scale look like they are potentially scalable. Ion traps are the example which has probably been studied most seriously with regard to scalability. And I think it probably would be possible by brute force to build a large ion trap that would be able to solve certain problems, like factoring problems that we can't solve classically. But it looks now like it would be very expensive. And so I think if society thinks this is an important enough problem to make a really big investment in it, it could happen in a few decades. But it's not clear that it's really worth the investment that would be required, which would be billions of dollars. And so I think part of the issue is, how badly do we want quantum computers for it to be worth the investment and the effort to develop that technology?